library for computational biology really developed here in the computational biology group over the last 11 years now. And a large part of it is open source tissue level cardiac simulator. So it's developed not for doing single cell or analysing different cell models, but for doing large scale electrophysiology simulations of whole organs. And so it's a parallel using MPI, finite element simulator for tissue level electrophysiology. And nearly from the beginning has supported the use of CellML for describing the cellular level model that's coupled to the monodomain or bidomain PDEs for the tissue level behaviour. And the Web Lab is built on top of it as an extension of CHASE that's focused particularly on taking protocols, applying them to different models and seeing what happens. But because we're building on CHASE, we've got all of that underlying functionality there. I'm going to talk a bit about some of that. So while CHASE was designed originally for tissue simulations, you can use it just as easily for single cell investigations. You can plug in any CellML model that you're interested in. You can code up in C++, whatever kind of experiment you want to apply to that cell model. Because we have all the parallel support for doing finite elements across multiple processes, we can actually exploit that to easily parallelize multiple independent simulations at single cell level. So you can run experiments on lots of different cells independently across all the processes that you have available. Makes it easy to scale up and doing lots of parameter suite type experiments. You've got all the CellML support that we've seen in the Web Lab for plugging in any model and interfacing with it in a consistent way that you can use. And because it's just a C++ library, you can do anything you like in C++. So it's more complicated to use in the Web Lab, definitely not the simple drag and drop kind of interface, but there's a lot more flexibility there. You can do anything that you can program. And there's a couple of papers you could look at. One that this is mostly focusing on is a paper we had in Frontiers in Physiology back in January this year, describes using CHASE for single cell cardiac simulations. And so most of the graphs, if you've seen the paper, you might recognize. But a summary of the key features that are useful in this context. I mentioned automatic use of CellML models, and that's on the fly. So you can bring in a new CellML model in a running simulation. There doesn't need to be any pre-conversion. And you can easily do a loop over different models. So you can evaluate different models in parallel or sequentially, bring them in on the fly, doing all the units conversion and doing the stimulus current conventions. All of that interfacing functionality that we've seen in the Web Lab is there as well. And there was a 2011 paper that went into that in some detail. You've got access to not just the state of the model, but also any model parameters, derived quantities, much as we've been doing in the Web Lab by just referring to ontology terms to access model variables. You can do the same thing from code in CHASE. You can give the local term for our oximeter ontology, refer to membrane voltage, and the model will give you membrane voltage, whether in this case that happens to be a state variable or a parameter or a derived quantity. Usually it's a state variable for a full-term model, but some things like calcium concentration may actually be computed. It may be a state variable. May just be a parameter depending on the model you're looking at. You can access it by name and you'll get the right quantity, whatever. And there's also a range of available solvers for running simulations of the model. When working with the Web Lab, it's always using CVODE behind the scenes to solve the ODE systems that you get. But there's actually a range of others built into CHASE, usually for single cell if you're wanting to use CVODE, but you can investigate quite a few others. One of the things we did was compare them. There's a few extra features. For instance, you can annotate variables, not just with their names, but to say things like this is a gating variable, this is a concentration, and hence should be between 0 and 1, or should be strictly positive. And the solvers will automatically enforce those, or at least give you an error if those constraints are violated, depending on the solver. With things like CVODE, where you can supply an analytic Jacobian to either give you a bit more speed or a bit more accuracy, we can actually compute those automatically using Maple, which can improve most models. Doesn't always work for many numeric reasons. Sometimes the Jacobians will actually have infinities or singularities in them, that if you've got the analytic form, that blows up much more easily than just doing a numeric approximation. And we can also do lookup tables for interpolating common expressions to avoid computing exponentials of v for a bit of extra speed, but a slight hit on accuracy. So as mentioned, we've got a range of ODE solvers. We've got simple cases, forward Euler, there's backward Euler one as well, that partially decouples particularly well in tissue simulations, Runge-Platter, and then Rush-Larson, both traditional and generalized Rush-Larson techniques are in there, which again, solvers for the ODE system developed particularly for a tissue context, but they're available for just doing single cell as well, and CVODE, which can be used both in single cell and in tissue context within CHAST. And punchline, comparing these, CVODE is always best for single cell, as you might expect. But in comparing the different solvers and various other features to work out what how is best to simulate particular models, you want to say, well, best for what? And we were looking at not just which ran fastest, but actually which would run fastest for a solution within a particular accuracy. And the accuracy measure we used, coming from Megan Marsh's thesis, I think a couple of years back, was mixed root mean square error. And so that combines both relative and absolute errors to give you a sense of how well your solution is matching a reference over an entire action potential or general time course. So we generated reference solutions with CVODE and very tight tolerances as our gold standard. And then for each model, for each solver that we were investigating, we successively reduced the time step until we got both the solver could actually solve and the system wasn't unstable, and the accuracy of the solution was within 5% on this MRMS metric, to say that's close enough. To give you a sense of what close enough looks like, so these are all solutions that are within that 5% error metric, and certainly from sitting in the back there, you can't tell any difference between those by eye. Even looking close up on a zoomed plot, there's very, very little variation between them for different solvers, but wildly different time steps that are producing that level of accuracy depending on the performance of the solver. If you go above that accuracy threshold, you start to get progressively different solutions. Possibly all of these are just with the generalized Rush-Larson methods. Other solvers don't tend to give you just bad solutions, they tend to just fall over if the time step is too big. You just get completely unstable and the solver crashes. Rush-Larson, very stable, but gives you quite varying solution quality once you start taking larger time steps. And because we can easily plug in any cell model, we can parallelize this, we can loop over solvers, we can just compare all of these two nested loops, say the solver and model, run for over 60 cell-ML models, different systems, and compare how fast the different solvers go. And as you'd expect for single cell, CVODE solvers here are both on average and pretty much always the fastest solver. And other solvers vary with similar sorts of speeds that we were seeing. The two variants of CVODE here are CVODEs with an analytic Jacobian supplied and with a numerical approximation to the Jacobian. And analytics slightly faster, but not by a significant amount. Compiler optimization is good, as you might expect. And one interesting point here is actually the blue line into production CVODE, which is the fastest line here. If you don't just use the default settings for CVODE, but actually recompile that with the fastest compiler settings you've got available to you, that does make a noticeable difference to simulation speed. So that's worth doing if you're doing a lot of single cell simulation. And then just looking in a bit more detail at the analytic Jacobian performance, you can't really see on the raw timings line, the analytic case is usually below. You can see it much better if you look at the speed up. So you're often getting about 10% to 20% speed up with analytic Jacobians as opposed to numerical Jacobians, except that some models you've got a gap here, it doesn't work, and for a couple of cases it actually makes things slower. So it's worth evaluating for your model whether that's going to be useful or not. And And then the lookup table optimization, which first did some 10 years ago during my doctorate. We've done a more comprehensive look at that over a range of different models and going for the same accuracy settings. And usually it's giving us around about a twofold speed up for the not so good solvers, not quite such a good speed up for CVODE. These lines on here, giving somewhere between 10 and 50% speed up most of the time, I think. So some improvement for same level of accuracy, but certainly not a massive amount. And again, you do need to check for your particular model whether that's going to give you the accuracy you expect for any given lookup table granularity. Especially if you're doing analytic Jacobians, you need much finer lookup tables on the Jacobian entries usually to get it to actually solve, because they're much less well approximated by linear functions. And I think the final one on timings, just to prove that actually you can use CVOD in a tissue simulation context, which went against received wisdom and said that actually the memory overhead and the adaptivity overhead would just kill you. It doesn't often, and especially if you've got a reasonably large PD time step of 0.1, graphs are really too small to see, but these are the CVOD solver lines here. They're not always quite the fastest, but they're always running, they're pretty much almost the fastest or the fastest, and for the more complex models, very much the fastest. So if you've got a reasonably complicated model, even in a tissue simulation with a relatively fine PD time step, it's probably worth using CVOD, just occasionally where it goes quite a bit slower. Most of the time it's either competitive or outperforming explicit methods, and even Rush-Larson methods as well. So that's just the general solving cellular ODEs and chased. There are a few extensions that give you extra functionality on top of that. And to chase the user project is the term we use, extension libraries that can just be added on to chased to give you extra functionality. And one called Simple Sensitivity I developed for John Wormsley a few years back when he was doing his doctorate here. And he basically wanted a way of running multiple different parameter sets for different models and seeing how sensitive the models were to variations in parameters. You could generate just CSV files of different parameter sets for a particular model, and you wanted to run all of those nicely in parallel and see what effects it was having on model outputs. So this particular project is just a way of letting you do that really easily. So you have a file defining the parameterizations, and the header of that file lists the names of variables with their ontology terms, so that you've got a way of having a parameterization that you can apply consistently to any model of the same system. You're not fixed on using one particular model. And it will automatically parallelize if you're running on multiple processes using the built-in chase functionality, so that if you've got 1,000 cores available to you, you can run 1,000 simulations at the same time. But in contrast to the web lab, where you've got a protocol defining in a somewhat restricted form what the experiment is that you're running, in this case, the virtual experiment you run is just arbitrary C++ code that can make use of any chased functionality. So it could be single cell simulations, and it was most of John's work, I think, but you could just as easily put in a simple tissue simulation in this context and parallelize those for different cell models or different parameter sets of your cellular model within a tissue simulation. So this is kind of balancing the abstraction that you get with the web lab with greater flexibility to do different kind of things, but still leveraging much of the same underlying framework to easily evaluate different models, different experimental conditions. Taking a slight sidestep, thinking about reproducibility, one of the things with the web lab is we hope it can be a community resource for what can the models do. If you've got these collections of models, what sort of behaviors can you evoke under different experiments? The community can add their models, add their experiments that they're interested in. Potentially we could add sort of extra community kind of features around that, such as commenting and explaining what's going on. But here's a yes, another simulator, simulating models, producing results. How much do we trust that? There are some features within the web lab itself that help. So all previous results are stored. You can compare if there's a new version of the model or a new version of the protocol or a new version of the software, what's actually changed with those results. But doing that isn't automatic. You have to do those comparisons manually in web lab as it is, which is less than ideal. The back-end simulator that runs experiments on the web lab is another Chase extension, a user project called Functional Curation. And that has quite extensive tests that are automated. So every time that software is changed by me or by anyone else, it's an open source project, there's a suite of tests that get run, both low-level unit tests, just of the individual functions and classes within that library, but also regression testing. So there's a suite of tests in there that run particular protocols on a range of about 30 or 40 models, and reference results are stored. Every time the software is changed, once a week, we rerun all of those experiments and check that the results are still within tolerance. So making sure that changes to the software are not changing the results of experiments, unless we can explain why, because we're fixing a bug. And then we've also got now an alternative implementation of that functional curation backend, which I'll mention more about later. But those two implementations are being tested against each other as well, to give extra confidence that we are actually really solving this protocol on this model, not just some spurious behavior from a bug in the software. And all of the results of these tests, as well as the source code, are public, so you can go and check that I'm not lying and it really is doing what they claim it is. And as with all the Chase software and other extensions, you can go install that yourself. And that's particularly useful if you want to run a lot of web lab experiments as well. Simulate it directly on your local machine. You can run many, many experiments quickly. So for testing out new protocols, that might be a quicker way of getting going, or if you want to run lots of experiments, you could do so locally on your own resources, rather than competing for community resources on the web lab. So, mention contributions to the web lab are very much welcome. It's quite a large project in terms of software now. There's a lot of code in there, a lot of code written in all sorts of different languages as well. So the current simulator, the Chase program is C++. The new implementation is in Python. There's already Python code in there for handling SALML, and all of the SALML interfacing stuff is written in Python. The website itself is written in Java on the back end, with a lot of JavaScript on the front end for doing the interactive stuff. So it's not necessarily the easiest thing to get started with, but I'm quite happy to give people detailed pointers if they would like to get involved and add. And all of the source code, the issue trackers, and everything are public, so people can at least keep an eye on development, even if they don't feel able to contribute. And in the next talk from Gary, we shall discuss a bit more about where we're planning to go with this. I think over to Gary.
Okay, so this was the picture we showed you yesterday, right at the beginning. And we talked about how the big missing thing from that picture is the experimental data. So you really want to link a protocol to some data, and if we've designed this system correctly, that should almost be a one-to-one mapping without too much messing around. So what would that enable? The first thing is just comparing the web lab results, instead of just against each other from different models, actually against some real life results. And then the rest of this talk will sort of discuss some of these bits, how we might assess what an experiment can tell us about parameters, how we might actually try and fit parameters. One thing that's been suggested by Turn, who's I did somewhere. So he's an experimentalist, and he'd quite like it if you read directly from his patch clamping software what the voltage protocol was, and you could just run that automatically. And really, we don't want to be storing all the data, and we want to try and link to some community repository for that. So now I'll just talk about a couple of little projects, big projects, sorry, that Ross and Kylie have been doing. So this is Ross's work. Just to give you an idea of the kind of scientific motivation for what we want the web lab to be able to do in the future. So Ross is looking at how much information is there in an action potential about the different ion channel conductances. So what we've got here in the green is a kind of modified canine action potential model, and the green is what you get when you just run the CellML file. There's some red real data there that's from isolated canine myocytes, just on different beats. So 3 different beat-to-beat variability kind of represented there. And then the blue shows what happens if we just let a minimizer try and change the conductances to replicate that action potential. You can see we get pretty good fits. Then the question is kind of how unique are those fits? Are those really the V conductances that could fit that, or how many different sets of conductances would fit? So we've been using Bayesian inference Monte Carlo methods for this. So you can kind of see what happens here. This is the likelihood, or kind of how well we're fitting the trace. So first we just run with a minimizer to get us in roughly the right area of parameter space. And then you allow a Monte Carlo Markov chain to run. And that explores all the possible, the idea is to explore all the possible parameter values and give them a probability. So you can see if we blow up this little section, we're actually jumping around in parameter space, looking at more and less likely parameter sets. So what comes out of that is a distribution for each parameter rather than a point value. So here they're kind of plotted pairwise as a heat map. So you think of this as looking down on the top of a histogram. And the dark bits is where there's the tallest, most probability. And this is what you get if you do the exercise I just showed you on simulated data from a simple Wiener-Reuter model. So there's only a handful of conductances. We're also trying to infer the noise that we put on the signal. And you can see this is what you'd really like to see. So the green lines are what the right answer was because we simulated the data with those parameter values. The yellow clouds are where we infer that the conductances should be. And we give them a probability. And then you've got a probability density function for each parameter. So this is what you'd like to see if pretty much pinned down. You can't look and see the numbers from back there, but you pretty much pinned down exactly what the parameters were. If we use a much more complicated model with sort of about 13 conductances in it, and we just consider one action potential, then obviously most of you would say obviously there's not enough information in one action potential to fit all those conductances. And sure enough, for certain conductances we infer a nice little small region of parameter space. For other conductances, especially in the background of pump currents and things, there's a great big spread. So from a single action potential, you can't give a background current conductance, as you'd expect. And that's not how you'd actually try and fit that if you develop a model. But this allows us to kind of attach some idea of which experiments should we be using to fit which parameters. And just as an example, here Ross is fitted to a single action potential for this. This is a sodium conductance. And then fitted to a kind of S1, S2 protocol where we stimulate a couple of times different frequencies. We get a bit more information. You can see the probability distribution narrows down closer to the true answer we used to simulate the data. With this is a background current. And it's much more dramatic, so we go from having almost no information to actually uncovering a bit about that. So let's talk a bit more about Kylie's project. So Kylie just got a PhD on all this stuff. And this is a bit more complicated. So now we're saying we're not even sure what the right model is for the HERG channel, the IKR channel. All these structures up at the top are published and Markov model structures for IKR. So which is the right one? How do you put all the parameters on all the rate transitions? These are the kind of protocols people use for activation, inactivation, recovery from inactivation. How do those link to the parameter values? How do those link to what your choice of model structure is? It's not really at all clear at the moment. So what Kylie's been having a go at is designing some new protocols. And this is a bit like the top two here are a bit like a web lab experiment. So we put in a protocol. In this case, we've designed some new sine wave based things. You get out quite a bewildering variety of model predictions. This is just all the published ERG models making very different predictions for this sine wave. And that's not an accident. We actually tweaked the sine wave parameters here in order to produce a range of behaviors from the models. So it's almost like a model, an experiment optimization to test the different which models. Well, to try and make reality choose one of the models over another, like optimizing it to test the hypotheses encoded by the model. And then down the bottom, Kylie went and did the experiments as well. And here's repeats for sort of 20 or 30 cells. And you can see that those are, whilst there's a bit of variation in there, they're a lot more consistent than the model predictions. And if we tie this into the same idea as what Ross was doing, here we've just assumed a structure and we try and infer the parameters that go on all these rate transitions. And again, we try and infer a distribution rather than a single value. And with the two different protocols, so the red ones are from the kind of traditional square wave protocols, which take kind of half an hour or more, and you'd be lucky to get them all done in a single cell. And the blue ones are from sine wave based protocols, which you can do in a couple of minutes. This is a simulated exercise. When we try and do this with real data, then these distributions don't end up in the same place. So there's something, a model doesn't seem to be able to replicate the behavior of reality in square waves and in sine waves. It will do one or the other, but then it won't predict the other one, which is pointing to some problem with the model structure or model structure. Okay, so I'll hand over to Aidan, who's going to talk a bit about a framework that might allow us to solve these sort of problems.
Okay. So I've been doing some work on my own user project, also building sort of off function curation. And the motivation for this was that, as we talked about yesterday, and we've been reiterating, virtual experiments are becoming very hard to replicate. Because we have remember our diagram where we were talking about how we feel published models sort of have experiments baked in and hard-coded. And we feel this is very much the same for parameter fitting experiments. Either when parameter fitting is performed, you don't report it well enough to replicate it independently, or when you publish your own code, it's so intrinsically tied to the problem at hand that it's very hard to generalize it and to reapply it. So, in a similar idea to what we do with functional curation, abstracting the notion of an experimental protocol from a model which captures just the underlying equations, we want to abstract the tasks of parameter fitting or model selection so that we can reapply them to new problems. So in this case, it would be very easy to share and update any kind of parameterized model when new data becomes available, to apply a successful fitting strategy to a similar study, and to in general, like we said, with what we're doing with Kylie, try a couple different protocols, models, and see which fitting schemes might work. So I think it would be a good advance. So if we look sort of at a visual representation, we see up top the sort of schema that we've been talking about with functional curation, where we've enforce the notion of model and protocol such that we can apply one to many, many to one, and it's all mediated by an ontology of terms. Or we just agree that certain model variables should have certain names, and the protocols will respect that, and that's how we do the linking. As Gary said, we also are concerned about matching outputs to experimental data, and this we hope to be one-to-one. If we have a well-designed experiment and the protocol output is well post-processed, then we should just get out exactly what we'd expect from a real experiment. So how do we do something similar for parameter fitting? So the concepts we have to work with are, again, models and protocols together. We combine them into the notion of a virtual experiment. So the input to this experiment would be the parameters of the model that we're trying to fit. So we start with some distribution over parameters that serve as the input to our experiment, which then generates output. This output is then evaluated against experimental data, and we decide if the parameters that we've input are close enough or need to be improved. So in this way, we can sort of loop, we can update our prior distribution over parameters through some sort of algorithm-specific decisions to update our posterior belief. So the way that we will do this, well, the way that I've been doing this is we sort of separate, so the experiment from the objective from the algorithm. These are all mediated by similar sort of ontological connections. So the data and the experiment are paired together because for whatever virtual experiment we have, there should be a physical experimental data that goes along with it. And we assume now that these will be one-to-one matching, and if we can hope that people abide by some naming conventions in an ontology, then the objective function really is just comparing two things that are very alike. We might imagine just two likely structured CSV files, or if you're in the Python framework, which we work now, dictionary objects that respect the same naming conventions. But we do allow for people to define their own ontologies. If experimentalists are returning data that they have named in a different way than your experimental protocol, you could set up a matching, talk about which variables match to which. So the objective function compares these two and passes its output to an algorithm. So the objective function can be applied to any matching set of experimental results and simulated results, and the output of the objective can go to any algorithm that we choose. There are some restrictions. For example, some algorithms, like the traditional least squares, will expect a distance function to minimize, whereas some things, like MCMC, will expect a likelihood function to maximize. So you can't completely match this, so I've drawn fewer arrows because you have to kind of understand what distance functions will work with certain algorithms and which ones will work best. That disappears for some reason. Okay. Anyway, slide animations. So one of the concerns that you may have is that if we look at the previous diagram, we've lost this distinction between model and protocol. We've combined them into the notion of an experiment, which is what we were sort of avoiding in the beginning. But this actually allows us to distance the concepts of an objective function and an algorithm. Basically, we're concerned from the algorithmic perspective with black box optimization. An experiment that takes parameters and outputs output, and we don't know how, we don't care how, because as soon as we get involved in that, it becomes problem specific and we can't apply the same algorithm to any other study. But under the hood, there are still a distinction between models and experiments, models and protocols in the function creation way. So without knowledge of the algorithm, we can swap them out. We can try different, for say, a case of Kylie's study, we can try different models for the herd channel under the same protocol and the output be otherwise. So objective functions, as we say, are comparing analogous experimental recordings to analogous simulation outputs, and this will be most generalizable if we have a sort of naming convention we respect. And finally, the algorithm combines the data, the experiment, and the objective function along with some prior beliefs of the parameter to generate a posterior. And there's one more sort of ontological connection here in that naming of the model parameters we assume will follow, it has to match in a certain way. So right now we're using the names that we attach in the RDF tags in a cell ML model, say, to be the names for our parameters so that the algorithm knows which parameters to link up to the model and to change. So this is the initial stage into my work. We would like, obviously, to extend this to the point that we have at the Web Lab where people could upload their own experimental protocols for parameter fitting, copy them, apply them to new studies. So I'll turn this back over now to Gary.
Yeah, so we've seen that we quite like to move away from point predictions and point parameter sets, which is something called uncertainty quantification in the kind of engineering literature. And that's one way to start to tackle all the variability that you find in biological systems. There's also, unfortunately, some kind of numerical uncertainty that comes into things. You can get quite chaotic behavior, and with complicated code like this, we've found things like not actually changing the mathematics, but changing the layout of the code changes how the compiler optimizes it, runs slightly different on a different machine. We really need to just make sure that all those kind of small numerical uncertainties are explored properly. And so we want to be able to look at the sensitivity of any results, any predictions to all the various uncertainties in the inputs, the parameters, the various things that are going to affect it.
In the case of chaotic systems, how do you compare an output to an experimental? You certainly can't use an L2 norm.
No.
Because your simulation may be going down when reality is going up, but it's still a very good simulation.
Yeah, I think you simply need to do enough realizations with plausible initial conditions and things to build up behaviors and compare that to experiment rather than a single thing. That's how we're. But yeah, all this is very, very much not solved problems. And we assumed that a lot of this would be when we started talking to stats people and mathematicians, but a lot of it is really difficult open problems. So where we're going with the Web Lab, ideally, instead of having our own copy of all the CellML files that are annotated separately, we would be pulling in directly from the Visio repository the CellML files and storing the annotations up there so that it's worldwide. Get the real expert on the model to annotate all the various bits so that we're not doing it wrong. And that would very much enrich the curation. So if you go onto the Visio repository, models are curated to ensure some kind of a standard, but usually the top level of curation is reproducing on paper. You really want to be able to reproduce them all. You really want the authors to kind of guarantee that they use that CellML file to do this stuff. Something about this. So SedML, we haven't really talked about SedML, but that's a community standard that's attempting to do almost exactly the same thing as our protocol languages. So it defines a simulation and some post-processing and plotting. So we use that as a start point. At the time we started, it was almost impossible to apply a SedML file to multiple models. So if you define a SedML simulation, you defined the model that was going to go into it. And so we had to kind of generalize that. And Jonathan's on the SedML board, and we'll be kind of feeding in the ideas and using this almost as a kind of test bed for SedML extensions. That SedML future versions will be able to do everything the Web Lab can do. We're quite aware that the protocol editing is pretty tricky at the moment, and so some kind of, even if it was just a nice text editor that highlighted the keywords and made sure you've not made any syntax mistakes in the protocol language, that would be good as well. In terms of technical stuff, at the moment things are still mostly C++ built on Chase. We're re-implementing that in Python. Hopefully this will make it a bit faster, which is normally the other way around, but for the n-dimensional array operations and things that have been done almost in a on-the-fly interpreted way, they're a bit clunky in C++. They'll work a lot better in Python. We're also aware that the n-dimensional array stuff is pretty tricky. So we're thinking about allowing you to drop into some kind of subset of pure Python to do post-processing with a few things to stop you doing remove all files. And we know the error messages are not very good, so we're trying to think how to make those friendly. And we're getting there with some of that. Aidan's done a lot of work on this Python way of doing things. So I think we're nearly there with my stuff. SLML files are brilliant, as we said at the start. And without them, we really can't share models very well at all. But they aren't enough to do everything that we've talked about in this session. We shouldn't be far away from automatically checking models against data sets, testing hypotheses, if you like. But I think in order to really be able to take a model out of the literature and use it in a sensible way, you need to have all the data that we used to train that model, all the protocols that we used to train that model, all the training algorithms need to be provided as well. And if you want to evaluate predictive power, then validation data and validation protocols. And so instead of a SLML file being the gold standard for what you publish to share your model, I think we need all of these things to go out and be there as part of a model, which is a massive shift if we actually, I'm not really aware of any so I haven't really given Jonathan enough and lots of work from these people as well. All these other people have been giving us feeding ideas along the way. So I think that's probably it for this session. We'll have a quick tea break, and then the bigwigs are going to give you a few thoughts on where they want to see the future of cardiac modelling going. And then we'll have a bit of an open discussion, try and get your ideas, or maybe whether or not anything we just said made any sense, and if it did, how we might be able to start as a community to try and work on it. Okay.